What I am going to talk about is motivated by the discovery of, more or less, and motivated by the discovery of 100% polarization in FRB, which is a tremendously strong constraint, because it in fact says that only one of polarization mode is radiated, which is very difficult to achieve. The idea is that 100% polarization could be naturally obtained in MHD system. Lorenzo already outlined this mechanism. Let us consider reconnection in the magnetically dominated system. It is well known that reconnection occurs via formation of what is called magnetic islands, which are in fact linear currents. They look like islands in the cross-section. These islands are formed each time merge, new islands are formed, and so on. Each merging of no, it is very difficult. Maybe stake is better. Merging is accompanied by this disturbance of the surrounding magnetic field. This is just a small disturbance with the characteristic scale of about the size of these islands, which scale with the Larmor radius of particles in the current sheet. Let us discuss this MHD noise. There are two types of waves: excited Alven waves and fast magnetosonic. Alven waves propagate along the magnetic field. The group velocity of Alven waves is along the magnetic field. Therefore, they could not cross magnetic field lines, and they remain close to the current sheet. And I'm not interested in these waves. Let us consider fast magnetosonic wave, which propagate outwards, and each merging event produces pulse, cylindrical pulse, which is seen on this simulation. Many pulses. Color here is Poynting flux. Width of the pulse is determined by the size of the magnetic island, which are 10, 100 times larger typically than Larmor radius of particles within the sheet. According to simulations, about 1% of the energy dissipated in the current sheet is converted in this sort of noise. And the main question is how this MHD noise is converted into radio emission. Fast magnetosonic wave is in fact sound wave, which longitudinal oscillation of plasma, just rarefaction and compression of plasma together with magnetic field. Magnetic field provides pressure. Inertia is provided by plasma and magnetic field in magnetically dominated system, and therefore velocity of the wave in highly magnetized systems is very close to the speed of light. These waves are longitudinal because oscillations are longitudinal along the direction of the wave. But electric field in this wave is perpendicular to the background magnetic field and to the velocity of oscillations. So this is transverse electromagnetic wave, which has phase velocity very close to the speed of light. And when plasma density goes to zero, it goes to the speed of light. And the conductivity current also goes to zero, because one could easily estimate that the ratio of the conductivity to the displacement current goes as 1 over sigma. Therefore, if this wave propagates towards the smaller plasma density, it becomes electromagnetic wave. Of course, eventually magnetic field also decreases, and eventually this wave meets cyclotron resonance. This is a real singular point, and we have to take care that at this resonance, optical depth is already small. Therefore, plasma density should decrease rapidly enough. I consider this in a special model in few minutes. So this is generally a mechanism which easily produces 100% polarized radiation, polarized perpendicular to the background magnetic field. The model was applied to emission from the crab and crab-like pulsars, and the question how it could be applied to FRBs. Of course, relativistic reconnection occurs in many astrophysical environments, but let us consider magnetars as one of the most favorable progenitors. And let us consider a model in details. Of course, in magnetars, there are many places for reconnection. First of all, magnetar flare is accompanied by a reconnection. But I doubt that this could reconnection well within the magnetosphere could produce FRB because, first of all microscopic scales, Larmor radius, and so on are very small deep inside the magnetosphere. Therefore, it is difficult to produce a 10-centimeter wavelengths. And the second problem, even if these waves somehow produce it, they could hardly escape. Because of nonlinear interaction of MHD waves, I consider this process in a few minutes. The better place is outer part of the magnetosphere, namely this current sheet, which begins at the light cylinder and separates oppositely directed magnetic field. The structure is similar to the structure of the pulsar wind. So let us assume that there is magnetar flare, which perturbs magnetic field and produces large-scale magnetic perturbation that propagates outwards in the magnetosphere. This is also a fast magnetosonic pulse. When pulse reaches current sheet, it compresses the sheet and pushes plasma with high Lorentz factor forward. This strong compression triggers fast reconnection. At the light cylinder, magnetic field in the wind is much smaller than the field in the pulse, if you normalize by reasonable luminosity of the pulse, so electromagnetic Poynting flux in the pulse. Total energy of the pulse, I choose more or less moderate value. So pulse propagate, this is background field of the wind. Here current sheet separating oppositely directed field. And when pulse arrives at the current sheet, everything is compressed and magnetic reconnection occurs here. Of course, such a laminar picture is highly improbable because such a sharp acceleration destroys the current sheet. Something like Rayleigh-Taylor instability is inevitable because plasma is accelerated, and one could expect not such a nice picture when a layer with oppositely directed magnetic field is just compressed and it is separated from the field in the pulse by current sheet. But everything is destroyed, and this flux splits into many tubes of oppositely directed magnetic field, and they fall practically freely inside the pulse. Why it is important? Because this layer is very narrow, because the layer of the size of the order of the light cylinder is compressed by many orders of magnitude. And therefore, if a reconnection occur here, the duration of the pulse is very small, about 10 microseconds and so on. But if reconnection occurs within the main body of the pulse, which is then duration of the pulse is determined by the length of the pulse, and it could be about millisecond and so on. In any case, all this energy of the oppositely directed magnetic field, all magnetic flux within the scale of about Larmor radius is compressed, and it is dissipated. Total energy dissipated is the energy of the field in the region of the light cylinder. It is increased by the amplification factor because everything is compressed, and some fraction of of this energy is radiated as a wave. This fraction is about 1% or something like this. In such a way, one could get a rough estimate of the total energy radiated, which is more or less gives a reasonable result. The second important quantity is radiated frequency. Again, wavelength is determined by the Larmor radius of the particle within the sheet. And it is something 10 times larger, about 100 times larger than this Larmor radius. Magnetic field in the pulse we know. Everything should be in the frame of the pulse. Thermal Lorentz factor, may be found by balancing energy released in the reconnection process with the synchrotron cooling. In this case, without fine-tuning, we get radiation in the gigahertz band. Therefore, we have a pulse duration about millisecond with this luminosity and this frequency. But as usual, if we discuss powerful radiation, the question is how this radiation could escape, if could. Important point that this radiation is formed in the pulse. Pulse propagates away with the speed of light. Therefore, these waves propagate on the top of this pulse. And everything goes far away from the magnetar until the pulse is decelerated when it enters either the termination shock of the pulsar wind or enters the previously ejected baryonic matter. Some barrier is necessary. When a magnetic pulse decelerated, radiation escapes. Lorentz factor of the matter in the pulse is determined very rapidly because, in fact, it's electromagnetic wave. Plasma moves in the crossed electric and magnetic field. In the pulse, electric field is equal to the magnetic. Total magnetic field is a little bit larger because magnetic field of the wind a little bit larger than the field of the pulse. Therefore, all plasma moves with the high Lorentz factor, about 100, with respect to the wind. The wind itself is accelerated. Therefore, pulse propagates very rapidly. Because the wave remains within the pulse, cyclotron magnetic field in the pulse is very high, and it decreases only 1 over r. Cyclotron radius is achieved at a very high distance, at very large distance. And here we could estimate optical depth. It depends on the plasma density, which could be conveniently normalized by magnetization of the plasma in the pulse. And optical depth is inversely proportional to the magnetization. The larger magnetization, the smaller amount of pairs. We see that cyclotron resonance is transparent if magnetization of the pulse exceeds few millions, which is not very strong constraint because the pulse is very highly magnetized. Another possibility is that wave escape from the pulse before cyclotron resonant radius is achieved. Either if radius of the termination shock of the wind is inside the cyclotron radius, which is possible if the pressure in the wind is large enough, or again, for repeater, if pulse collides with the previously ejected baryonic material, which could happen far from the magnetar, but distance smaller than this. So, in principle, cyclotron absorption is not very dangerous for this process. Another absorption mechanism is nonlinear interaction of waves, because we deal with MHD systems. And the most dangerous interaction is three-wave interaction. In fact, a decay of fast magnetosonic wave into fast magnetosonic and alveonic, or into two alveonic waves. The rate of this process is, as usual, proportional to the frequency of the wave. Everything is the frame of the plasma. And the ratio of the amplitude of the wave to the background field squared, which is, in fact, ratio of the luminosity of waves to the luminosity of the pulse. Important point that these processes are induced. Therefore, new waves are emitted into states where already radiation is available. Because alvean waves are absent from the beginning, they should grow from initial very low level. And therefore, we need about 10, 20 e-folding time in order to, for this process become efficient. Therefore, condition for the wave to escape without being affected by nonlinear interaction is just rate of interaction multiplied by available time. This optical depth should be smaller than about 10 or something like this. estimated this optical depth, we get something like about unity, which is more or less smaller than 10. But this is small only because everything occurs in the very fast pulse. Within the magnetosphere, magnetosphere is static. This process is much more important, and that is why I hardly believe that these waves could escape from the magnetosphere. They are absorbed by this three-wave interaction. Another processes are not important. Nonlinear steepening induced scattering, which occurs only beyond the cyclotron resonance. So waves could escape. And the last point, polarization. Polarization is 100% perpendicular to the background magnetic field. In the pulse itself, the magnetic field pulse drags magnetic field from inside the magnetosphere. Because this is wave, slowly this magnetic field is substituted by new plasma and magnetic field coming from the wind, and old plasma and magnetic field escape backwards. But because everything is dragged with very high Lorentz factor, this substitution process is very slow. Even at the cyclotron resonant radius, only small fraction of the flux is substituted by the magnetic field of the wind. Why is it important? In the pulse, magnetic field is directed somewhere which is determined by the position of the flare. In the wind, field is azimuthal. Therefore, if this layer is accumulated, wave escaping forward pass this layer azimuthal plasma and become polarized along the rotational axis of the pulsar. One could check that the condition of adiabatical adjustment of the polarization plane in this case is fulfilled if waves escape before the cyclotron resonance is achieved, which is quite possible. In this case, we get 100% polarized radiation, polarized along the rotational axis of the magnetar. If not, we could expect depolarization. If adiabatic adjustment is impossible, wave polarized perpendicular to magnetic field here, split into local normal modes, and degree of polarization decreases. In principle, one could even speculate that if, in this case, one could expect, in some cases, even sweep of the direction of polarization, but this should be discussed more carefully. Okay, I think I'm in time.
No, you're -4 minutes now.
Okay, therefore, here my conclusion. Thank you.
Okay.